screen. Okay. I can see, oh, too small. I can see where we left off last time. Okay. So I'm going to try out this matrix vector multiplication. So the top entry will be 1 times 1 plus -2 times 2 plus 1 times 3. The second entry will be 0 times 1 plus 2 times 2 plus -1 times 3. And the third entry will be 2 times 1 plus 1 times 2 plus 1 times 3. So what does this work out to be? 1 minus 4 plus 3, 0. 0 plus 4 minus 3 is 1. And 2 plus 2 plus 3 is 7. So that's an example of matrix vector multiplication. Now, let's see, is there anything else that I want to show? Vector addition. So we can add 2 of these n by 1 column vectors together as long as they have the same dimensions. And their sum is component-wise. This is just how we define vectors, and it's, well, all examples of vectors that we've seen before work exactly like this. Matrix vector multiplication has a distributivity, so we can distribute it multiplication across addition. A times x plus y, so we're adding together 2 vectors and multiplying a matrix by it. As long as the dimensions work out, then this will distribute just as ax plus ay. And also, if we add 2 matrices together and multiply it by a vector, we also get that it distributes. I won't go through a formal proof of these. You can sort of see how the details of multiplication work, and you would see that this works out just like you would expect it. We've talked before about the identity matrix. This is a special matrix that has 1s along the diagonal and 0s everywhere else. So the 2 by 2 example of this was 1, 0, 0, 1. The 3 by 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1, and so forth. This is a special case of a more general type of matrix called the diagonal matrix. These entries right here are called the diagonal of a matrix. And if all of the non-zero entries in a matrix are just on the diagonal, then it's called a diagonal matrix. I think I'll have an example of using these in the solution of a system of ODEs in a bit. Now, let's use the notation of matrices and vectors to organize our system of linear first order ODEs as a matrix vector equation. So what we had as our system was x1 prime equals, and then there's the coefficients, which we were taking to be general functions of t. So x1 is our first variable, and then a coefficient multiplied by x2, our second variable, all the way up to our total number of variables n. Then we have x2 prime equals p21 of t, x1 plus p22 of t, x2 plus dot 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 plus p2n of t, xn. And this continues all the way down to our nth variable. Its derivative, we're taking the variables to be functions, pn1 of t, x1 plus pn2 of t, x2 plus dot 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 plus pnn of t, xn. Now this would be the homogeneous version. The non-homogeneous version, we would have an additional function just in terms of t. We call this one g1 of t, g2 of t, gn of t. So this is the general system of linear first order ODE. So this is the kind of thing that we're considering. Now, if we collect together all of our xi's, into a vector, we'll call that vector x, and it will be x1, x2, all the way down to xn. So we can think of x of t as we just plug in t for each of the components and we get the value of that component. So this is a vector valued function. We can think of it as collecting together all of our functions of a single variable with a single output, or we can think of it as now a function that outputs a vector if we input a t. So this is of a single variable t. Okay. Now we can define the derivative of x in the same way that we did in Calc 3, for example. So the derivative is just done component-wise. So x prime, this will be x1 prime, x2 prime, so the derivative of each of its components, all the way down to xn prime. And what we see is that if we were to take our coefficients here, we can form a matrix out of those and write this whole system as a matrix vector multiplication. So that matrix we'll call capital P. We typically use capital letters to signify matrices. And this will be P11. And I'm going to emphasize for the moment that these are functions of t, simply by writing P11 of t, P12 of t, all the way over to P1n of t, and then P21 of t, P22 of t, all the way over to P2n of t, and then going down all the way to Pn1 of t, Pn2 of t, Pnn of t, going down, and then all the way through the matrix. And this is what we get for capital P. And so if we write x prime equals px, this gives us exactly the homogeneous part. You know, let me do this. Whoa, what? I'm saying what, but I should expect this to happen by now. This is the homogeneous part of our system of equations. And what we get is this matrix vector equation, right? We've got a vector equal to this matrix multiplied by a vector. And that allows us to summarize our entire system of, at least the homogeneous part of our entire system, in terms of just a matrix vector equation. Now we can include the non-homogeneous part here by just collecting together d of t is equal to g1 of t, g2 of t, all the way down to gn of t. And now we have our general thing here. Now, one thing that might be interesting to note is that we can think of this p now as a function of t. All of its components are functions of t independently. And so when we plug in a t, we get a matrix. So this we can think of this as a matrix valued function. It takes in a number t and outputs a matrix. Well, that's just this matrix here. Okay. So that allows us to organize this. And what we're going to start off with is just what we had started off with in previous versions of this problem, and that is start off with just the homogeneous version. Okay. And in fact, let's go straight to something concrete. Let's start with an example of an example of the homogeneous version with constant coefficients. We'll just go straight into this. Let's look at an example of that. Now, when we have constant coefficients, the matrix P will just be some matrix. And so we can specify our problem just by writing something like this. So let's give an example matrix. X prime. I have no idea what that noise is, but go with it. So here's our matrix. We have X prime is equal to that matrix times X. I think it's coming from outside. Let me close it. I don't mind the cicadas so much, but whatever that high-pitched noise is, it bothers me. Okay. Now, let's take a step back first. So a little aside, a little reminder over here. If we only had one equation in our system, then this was something that we had done before. This was just dx over dt is equal to some constant times x, right? So that if we just have one equation, this is a 1-by-1 matrix, it just reduces to this situation we've seen before. And these had the solution x of t is equal to c e the at for some constant c. So this was our general solution. So let's guess that our solutions will be of the form e to the rt and see what we get. See if we can find a solution. And one thing I didn't note, and I'm going to kind of do this without proof, is that when we had the nth order linear homogeneous equation, our general solution involved just linear combinations of a fundamental set of solutions. And if it was nth order, then we had two fundamental solutions that we wrote everything else in terms of. Multiplied the first one by a constant, the second one by a constant, added them together, and we get all the possible solutions. That works the same way in systems of equations. So a system of n homogeneous linear first order. A lot of times people write first order linear homogeneous. I wrote it in the reverse order. I don't think it really matters. So a system of n homogeneous linear first order ODEs will have a fundamental set of n solutions, and all the other solutions will be linear combinations of those. Okay, so I'm just going to state this without proof, and we'll jump straight into actually solving some of these. Now, once we have these n homogeneous, and we have these n fundamental set of solutions, fundamental solutions, then we will know that we have all of the solutions by looking at the fact that existence and uniqueness theorem allows us to say that this is the solution for a given initial value set of initial value conditions. So once we have this solution, we know we have these solutions. So if we can guess that the solutions are of a certain form, and then we get the solutions, then we know that we've guessed correctly. We've got it right. Okay, so what do we get if we have, let's say, x is equal to e the rt let's see, how should I write this? Let's say that our proposed solutions x of t are equal to a e the rt, where a is a vector. Actually, I can just write this out. Let's call it a1, a2, e to the rt. This is the extension of the assumption that we made before, right? So if our solutions over here are of the form c e to the at, then just generalizing this c, well, let's just call it c. Continue to call it c. Why not? In this case, it'll be c1, c2. Now, you know what? I'm going to stick with A because later on I'm going to want to use C for something else. I could use A instead. Yeah. Anyway, we're going to assume that our solutions are of this form, and so x prime of t will be equal to r a1, a2, e to the rt. And so if we plug this in over here, what do we get? we will get, plug it into this, the equation that we're trying to solve. Get x1 prime, x2 prime equals 2, 0, 0, minus 3 times a1, a2, or t, and x1 prime, x2 prime will be let me take a step back. I'm getting a little bit ahead of myself. This is a special situation. We're dealing with a diagonal here. Let's just go straight to just trying to solve this. So what happens when we multiply this out? We get, this is 2 times x1 plus 0 times x2, and 0 times x1 plus negative 3x. Well, this is just 2x1 minus 3x2. And what we get from this is x1 prime is equal to 2x1. x2 prime is equal to negative 3x2. And we already knew how to solve these. We got x1 is equal to e to the 2t, and x2 is equal to e to the minus 3t. And this formed our fundamental set. So e to the 2t, e to the minus 3t. Okay. So if we write out our general solution, x of t, this will be some arbitrary constant times x1, so d1 e to the 2t, some arbitrary constant times x2, that's e to the minus 3t. And we can write this as c1 e to the 2t 0 plus c2 0 e to the minus. And if we pull the scalar function out of each of them, then what we get is c1 times the vector 1, 0 e to the 2t plus c2 0, 1 times e to the minus. So that's how we can represent our solution. So our two vectors that represent our fundamental set of solutions will be this one and this one. Now we can do a similar thing here to what we did before, which was to determine if these are independent from each other. And the sense that we use of independent here is we also call it the Wronskian, but it's just going to be basically stacking these columns together and looking at the determinant of the matrix. So the matrix will be e to the 2t 0, 0, e to the minus 3t. And we're going to compute the determinant of this to get the Wronskian. And that will just be e to the 2t minus e to the 3t, which is e to the minus t, minus this diagonal here. So we remember how to compute the determinant of this. So this is non-zero. And so we conclude that 1, 0 e to the 2t and 0, 1 e to the minus 3t are independent and thus give us our fundamental set of solutions. So these are two values of x for this equation. Let me just rewrite it here. What were they? 2, 0, 0 minus. Just 4 more classes. X prime is equal to 2, 0, 0 minus 3 x. So we have two independent values that we can plug in for x here and here that give us solutions. And so all of the solutions can be written in the form of those. Okay, let's look at another example. So this is a matrix 1, 1, 4, 1. And if we take x equals, call it a1, a2 times e to the RT, we compute the derivative of this, r a1, a2, e to the RT. We plug this into our equation. What we get is r times a1, a2 equals e to the RT equals 1, 4, 1, 1 times a1, a2 e to the RT. Now we can cancel out the e to the RT on both sides because that's never going to be equal to 0. And what we end up with is this interesting kind of matrix vector equation. So 1, 1, 4, 1 times our vector a1, a2 equals r times our vector a1, a2. So what we're looking for is vectors for which multiplication by the matrix, I'll call this matrix A, capital A, is equivalent to simply scaling the vector. And I'm going to give the vector a name. I'm going to call it V. So what we're looking for is vectors that when this matrix acts on them, when it acts on them by multiplication, that action is simply to just scale the vector by some amount. And this is an example of a problem, a more general problem. It comes up in ODEs, but it comes up very broadly in linear algebra, and linear algebra its use is so widespread throughout all of mathematics, basically, and through the sciences, um, that we consider this to be sort of a fundamental problem when we look at matrices. And this is called the eigenvector eigenvalue problem. So we're looking for AV equals RV, where this is a matrix. V is a vector, and R is a scalar. And we're trying to find the eigenvectors. These are the non-zero vectors, and the corresponding eigenvalues. These are corresponding scalar R, which satisfy such an equation. And these are of fundamental importance throughout mathematics. Every area of mathematics, somehow you will see eigenvectors and eigenvalues pop up. For some reason, it seems to be a sort of a fundamental thing. Okay. Now, first of all, I want to say something about this non-zero here. If we plug in 0 for v, the 0 vector being vector with all zeros, we're always going to get as an output of that multiplication 0. And so we'll always have a corresponding eigenvalue of 0. Now that's the trivial solution. So we're looking for the non-trivial solution. We're looking for the ones that aren't just 0 and the vector 0. So I think there are problems already on the final exam where they ask you to compute the eigenvector and eigenvalue for a particular matrix. So we're going to work through how to do this. Now we can use the distributivity of matrix multiplication in order to find a solution to this. So the first thing I'm going to do, I want to, how would we normally solve something like this? We would try to subtract this thing over to one side, factor out the v, and figure out what v gives us the answer that we want. Now we can't do that because we have a matrix here and we have a scalar here, and we can't really combine those together. So in order to do that, what we're going to do is we're going to take this R and turn it into a matrix that has the same property. So R times V scales every component of V by R. I want a matrix that does the same thing. And the matrix that does that is going to be a diagonal matrix where every entry is just R. So that will actually just be R times I. It's a matrix R times I. V does the same thing. In the 2 by 2 case, Ri will just be R0, 0, R. And if you do the matrix multiplication, you'll see that you get exactly scaling each component by just R. So first we have AV equals RI V. For the parentheses here are really unnecessary. It's just to emphasize the fact that I'm forming a matrix here. Subtract it over to the other side, I get AV minus RI V is equal to 0 by what we already know about matrix addition and subtraction. And now distributivity allows me to say that this is equal to A minus R I B equals 0. So now we've transformed a problem where we're looking for these eigenvectors and eigenvalues as a solution to this. Now they're solutions to this equation where one side is equal to 0. And this brings up another interesting property of matrix multiplication, which is that sometimes you can multiply two things together which are non-zero and still get 0. That's another way that this sort of abstract multiplication differs from our ordinary multiplication. We have zero divisors. We have things that you can multiply, non-zero things that you can multiply together that are 0. Now, we already had this notion, and let's recall, at least for the 2 by 2 matrix. We had a 2 by 2 matrix, general 2 by 2 matrix like this. We've already seen that we can do an inverse of this matrix, right? We can get a matrix that if we multiply it by this thing, we get the identity matrix. And that matrix was, we denoted it by A inverse. It was D A negative C negative B divided by the determinant of A. And the determinant of A was equal to AD minus BC, right? Now, if we have an equation, AX equals B, then we could solve it by multiplying both sides by the inverse, like this. This became IX, which is just X. And this side was just A inverse B. So solving this system of equations, or solving this matrix vector equation, would simply involve computing what the inverse was and then multiplying it by the other side. Now, if this other side is 0, then what we always get is X equals A inverse times 0. It'll just be 0. So we only get the trivial solutions this way, which means that there must be something going wrong when we multiply by this inverse. In order to get non-trivial solutions to the B here, well, you're just taking it on faith, maybe at this point, that there are non-trivial solutions to this. But we can see that there is actually something that goes wrong, or could go wrong, and that is that 1 over the determinant of A, this division by determinant of A. If the determinant of A is 0, then we can't form the inverse matrix. So this is something that could possibly go wrong, and this is in fact what happens. Like I said, not going into all of the theoretical details. You will take 322 soon enough, and you will see all the details for that. So I'll just make it a statement. So let's say, let's write it over here. AX equals 0 has non-trivial solutions exactly when the determinant of A is equal to 0. If the determinant of A is equal to 0, we have non-trivial solutions. And if we want to force there to be non-trivial solutions, we must have an A that has a determinant of 0. Okay. Now that gives us a way to solve a problem like the one we were looking at. We wanted to find, I was just trying to remember this matrix here, 1, 4, 4, 1. So we had 1, 4, 1, 4, 1, 1, like this. A1, A2 is equal to R times A1, A2. This was precisely the eigenvalue eigenvector problem. If we can solve this thing, then we can figure out the value of R. That will be our eigenvalue. It's useful for getting used to the namings all of these things before you have to take it. Like I said yesterday, 322. That was when I took it as an undergrad, because I actually went to UK as an undergrad. When I took 322, that was the first time I'd ever taken a math class in my life. And I panicked because it was like a totally new way. I'm not kidding. It was a totally new way of doing things. And it was the first time I had ever felt like I was just completely lost. And I had to really bear down and work on orienting myself and getting used to it. And a lot of students have that feeling when they first go into the class. Very common thing. Okay, so we're solving this eigenvector eigenvalue problem for this particular matrix. So these are considered to be fundamental properties of this matrix. In a certain sense, if you know, well, actually, exactly, if you know the eigenvalues and eigenvectors of a matrix, you can reconstruct that matrix just from that data. So it contains all the information about the matrix. Anyway, let's try to solve this. We're going to have 1, 4, 1, 1 times A1, A2 equals R0, 0, R times A1, A2. This is our Ri, right? Subtract it over the other side and factor it out. I'll do this in one step. We get 1 minus R, 1 minus 0, 4 minus 0, 1 minus R. A1, A2 is equal to 0, 0. And now we're hunting for those situations where we have a value of R so that this inverse does not exist. So that's exactly when the determinant is equal to 0. And we know the formula for the determinant. It's going to be this diagonal. So 1 minus R times 1 minus R minus 4 times 1. In other words, 1 minus R squared minus 4, or R squared minus 2R plus 1 minus 4, which is R squared minus 2R minus 3. Assuming I haven't made any mistakes in my arithmetic. I don't think I have. And we want this thing equal to 0. Now, just like in the second order linear ODEs, when we had the characteristic polynomial, right? Again, we have our characteristic polynomial here. And this is called the characteristic polynomial. Either we could say it's the characteristic polynomial of this matrix, which in fact we do say that, or we could say it's the characteristic polynomial of that system of equations. Or if we looked at the equivalent second order linear differential equation, we would get the same characteristic polynomial. So these are all related to each other. And so it's natural to give them all the same name, the characteristic polynomial. And just like in that case, we're going to solve for R to find the roots. It was no accident that this letter here was R. And so this is equal to R minus 3 times R plus 1. And we get R is either 3 or negative 1. All right. So we have our eigenvalues, exclamation mark. We have solved a simple version of the type of problem you will see in 322 about halfway through the semester. Okay. So what do we do with these eigenvalues? Well, that's going to give us our R1 and R2 for the e to the RT. We just need to find the vector now. And that vector is this A1, A2. Now this is going to be easy because when we take this eigenvalue, let's take the first eigenvalue. Let's say eigenvalue number 1, r equals 3. When we plug that into the matrix, what do we get? 1 minus 3 is -2. 1, 4, -2. A1, A2 equals 0, 0. And what we see, we can multiply this out to get a system of equations. Minus 2a1 plus a2 is equal to 0. And 4a1 minus 2a2 is equal to 0. And you'll see that these two equations are equivalent, right? You can get the second one just by multiplying the first one by -2. So that doesn't contain any additional information about A1 or A2. Now, what this means, if you recall from earlier times that you've seen systems of linear equations, is that one of these variables is going to be arbitrary, and the other one will be determined in terms of it. So we have, for example, A2 is equal to 2A1, and this will give us all our solutions. And so we can pick an arbitrary A1, and our A2 will be determined by that. And this actually corresponds just fine with our original problem, which is right here, when we're trying to figure out an eigenvector and a corresponding eigenvalue. Because if we take some constant and multiply it by this, let's say gamma, we multiply gamma by both of these vectors, we've just multiplied a constant on both sides of the equation and nothing has changed. So an eigenvector is not unique. We get a particular eigenvalue, but the eigenvector associated with it is not a unique eigenvector. It's up to a scalar multiple. So any scalar multiple. So we just pick one eigenvector, and that's going to be fine because at the end, going back to our previous problem, we know how it's going to end up. I think I was going to scroll back this far. What was am I missing something? Oh, here we go. We're going to have an arbitrary constant multiplied by both of these solutions anyway. So it doesn't matter that we just pick our constant arbitrarily because it's going to be multiplied by a constant in our general solution anyway. So we're going to pick our eigenvector corresponding eigenvector is going to be the first entry A1 is going to be 1, and that means our second entry A2 is going to be 2. So we get we don't write it like this. So x1 is going to be the component. We'll write the individual solutions. This is our first solution that we've come up with by this method. So something that solves this, that satisfies the system of equations is the vector 1, 2 times e to the 3t. So that's our first solution. Second solution, eigenvalue number 2, r equals -1. We plug this in. What do we get for our matrix? So it's 1 minus r, so that's 2. And then no. Okay. 2, 1, deep breath. 4, 2. That's our matrix. A1, A2 equals 0, 0. And so, of course, this gives us 2a1 plus a2 is equal to 0, or 4a1 plus 2a2 is equal to 0. this is exactly what we expect to happen. We expect this system of equations that we get from this to not be independent. And you'll see in a little deeper detail in matrix algebra why this is the case. But basically, when we have a determinant is equal to 0 and we don't have an inverse, then there's not enough information in that system to pin down a single solution. So what we end up with is a system of equations where we don't have independent equations. So I'm just writing down one of them. And what we get from this is that A2 is equal to negative 2A1. So we can pick our solution, our corresponding eigenvector. That will be, I'm going to choose 1 for A1, and that becomes negative 2 for A2. And so our second solution, which I'm writing this, x2, 1, negative 2, e to the minus t. And what we get for our general solution is C1, 1, 2, e to the 3t, plus C2, 1, negative 2, e to the minus t. The book actually goes into a lot of detail about qualitative information that we can get about a solution. And it's actually really nice. I really do recommend this textbook a lot by a lot over the other textbooks that we've been provided for this class. It's a good idea to read this stuff just on your own. Just kind of challenge yourself with this. How much understanding can you are you able to pull out of this textbook? It's a good exercise, good mental exercise. Okay, another example. How much time do I have? Oh, about 5 minutes. Well, okay. So what we've done today, I'll go ahead and write up the example and we'll work this. But this is enough. This is enough about the problem to start on at least the first few problems of the web work. Now I'll go ahead and say, now let's solve this one first. Let's go ahead and solve it. We want the eigenvalues and eigenvectors of this matrix. That's what we're going to ultimately be solving, right? So that's going to be the thing that we're trying to do, and we'll go straight to doing that. So we're going to find when the determinant of negative 3 minus r, square root of 2, square root of 2, negative 2 minus r equal to 0. Now we'll get the characteristic polynomial for this matrix, and that is negative 3 minus r times negative 2 minus r. There's a negatives that I can get rid of there. And then minus square root of 2 times square root of 2. So this is equal to, just simplifying a little bit, save myself a little headache. Six plus 5r plus r squared minus 2 is r squared plus 5r plus 4. I messed that up? No, I didn't. Hey, small victory. So this is factors as r plus 4, r plus 1. Excuse me. And so we get as r negative 1, negative 4. And if we plug these back into our A minus Ri matrix, we get for negative 1, So that's the first case. Negative 4, square root of 2, square root of 2, negative, oh, no, made a little mistake there. Negative 3 minus negative 1 is negative 2. Negative 2 minus negative 1 is negative 1. A1, A2 equal to 0, 0. And really, we only need the first one, negative 2A1 plus square root of 2A2 equals 0. So square root of 2A2 equal to 2A1. And I can divide both sides by square root of 2 and get A2 is equal to square root of 2A1. So the corresponding eigenvector will be I hate this. Okay, 100%. That's closer to 60% than 10%. You know, what I'm really dreading, like my nightmare scenario, is the Delta variant really takes off. And in the fall, I have to teach online classes again. I can't handle it. I think I'll just quit. I'll become what? I'll become something else, an Uber driver or something. Anyway, this is our vector, our eigenvector, and then we get e to the minus t. That gives us our exponential component. And so our first solution is this. And now our second one, r equals negative 4. So this is 1 square root of 2, square root of 2, 2. A1, A2 equal to 0, 0. And so from this we get A1 plus square root of 2 times A2 is equal to 0. And so I guess in this case, I'll make A2 be my arbitrary thing. So A1 is equal to negative square root of 2A2. And so what I'll get for my eigenvector is a 1 for A2, and that gives me a negative square root of 2 for A1, e to the minus 4t. This is my second solution. Okay, and so I've run out of time for this, but what we might be interested in checking is the Wronskian. So if we do e to the minus t square root of 2 e to the minus t, so that's our first solution as a column, and then minus square root of 2 e to the minus 4t e to the minus 4t, and we compute the determinant of this. Is this equal to 0? Now there's a section in the book. Let's see. This is 7.5. So section 7.4. They have a theorem called Abel's theorem, and that theorem gives us the ability to, instead of checking the whole Wronskian, so computing these functions all multiplied together and added and subtracted, we can just compute it at a particular value of t. And if it's non-zero at that particular value of t, it will be non-zero in the entire interval that we care about for the existence and uniqueness theorem. So that's a useful tool. Now, I want to say really quickly before I end the possible things that can go wrong. The first case, the nice case that we've been dealing with, is that we have distinct real eigenvalues. Now remember, these eigenvalues are coming as the roots of a polynomial, and so the roots could be real or they could possibly be complex. So that's the next possible scenario. The next possible place where this could go wrong is we're going to say still distinct, but complex eigenvalues. And so we've actually seen what happens if we, instead of having a real value here, we plug in a complex value into an exponential. We end up with sines and cosines, right? We've seen that before. We end up with oscillatory solutions. The final case is when we have repeated eigenvalues. And this turns out to be, it's basically the same situation. We had repeated roots for our characteristic polynomial. In the previous cases, when we had a single nth order ODE, and that is that we'll have powers of t multiplied by our exponential. Anyway, this stuff we'll see some examples of tomorrow, and then maybe a little bit more on eigenvalues and eigenvectors and matrices. For today's Wednesday, right? Okay, so we've got Thursday and Friday, and then I think Monday I'll just do as sort of a review. The final exam is going to be series solutions and systems of ODEs, and that's it. So that's going to be the final exam. So we can spend Monday doing review and practice stuff. And then Tuesday will be the final exam. I'll have it open Monday and Tuesday, or maybe Sunday, Monday, and Tuesday for people who want to take it at different. Anyway, and that'll be it. That'll be the class. All right. All. Thanks.